In our last module, we have seen the large sample distribution of sample skewness coefficient, and we have seen how to obtain such a distribution starting from the joint distribution of sample central moments. In this module, we start with finding the large sample distribution of sample Cartosis coefficient. Then we shall discuss one interesting result in large samples, that is, for normal parents, sample skewness coefficient and sample Cartosis coefficients are independent. Then we pass on to some bivariate distributions and find the large sample distribution of correlation coefficient, that is Pearson's product moment correlation coefficient for bivariate distributions. And finally, we shall discuss, or better envisage, the different properties of the distribution of correlation coefficient when the parents are bivariate gamma, multinomial and bivariate normal. So we start with distribution of sample Cartosis coefficient, that is large sample distribution of sample Cartosis coefficient. Suppose xn are IID random variables with finite 8th order moment mu8. If we denote the rth order central moment by mr, then the population Cartosis coefficient can be defined as gamma 2 equal to mu4 by mu2 square minus 3, provided of course mu2 greater than 0. As earlier, mr, that is rth order central moment obtained from the sample, is a consistent estimator of mu r, that is rth order population central moments, and hence a consistent estimator of gamma 2 is G2, which is defined as m4 by m2 square minus 3, of course when m2 is positive. Then G2 is a function of two sample central moments, namely m2 and m4. Now to derive the asymptotic distribution, we define GUV as u by v square minus 3, which is continuous and has continuous derivatives except at u equal to 0. And we note that for u equal to 0, this Cartosis coefficient is not defined. Now from the joint asymptotic distribution of the sample central moments, we have the large sample distribution of m2 and m4 as a bivariate normal with mean 0 and dispersion matrix sigma, where sigma has elements sigma 22 and sigma 24 in the first row, and because of the symmetry we only need to consider the next diagonal element for sigma, which is sigma 44, and this sigma 22, sigma 24 and sigma 44 all are defined in our previous modules. Now a straightforward algebra gives the first the gradient vector of G evaluated at mu2 mu4 as a vector with two components as minus 2 times mu4 divided by mu2 cube and mu2 to the power minus 2. Therefore, using the previous results and delta theorems, we obtain the large sample distribution of G2 as again a normal with mean 0 and variance sigma 2 square, variance tau 2 square, where tau 2 square is can be evaluated as gamma 2 plus 3 whole square multiplied by some function of mu2, mu3, mu4, mu5, mu6, mu7 and mu8. Now as earlier, we referred the interested reader to the book by Surfling for an explicit expression of H. However, the expression is quite cumbersome. Now if the underlying distribution is standard normal, we can take this distribution as standard normal because our Cartosis coefficient is independent of location and scale. So we can use some distribution which is independent of location and scale, and as a consequence we consider standard normal distribution. Then due to symmetry of normal distribution, all odd ordered central moments are 0, that is mu3, mu5, mu7 are all 0, and using some relation, some properties of standard normal distribution, we find that mu4 equal to 3, mu6 equal to 15 and mu8 as 105. Then we obtain the large sample distribution of G2 for normal parent as again normal with mean 0 and variance 24. Next, we consider an interesting aspect of sample skewness and sample Cartosis coefficient in terms of asymptotic results. We shall find the joint asymptotic distribution of skewness and Cartosis coefficients. As earlier, we assume IID random variables with finite 8th order moment mu8, and we have already defined G1 and G2, gamma 1 and gamma 2, so we are not repeating the definition. But to obtain the asymptotic joint distribution of such coefficients, we need to define a vector valued function G. So we have a G function which is a function of u1, u2, u3, and this G function is itself a vector with two components G1 and G2, where G1 is u2 divided by u1 to the power 3 by 2, and G2 is defined as u3 divided by u1 square minus 3. As indicated earlier, each Gi is continuous and has continuous derivatives except for u1 equal to 0. Now, from the joint asymptotic distribution of the sample central moments, we have the joint asymptotic distribution of M2, M3 and M4 as trivariate normal with mean 0 and dispersion matrix sigma, where the elements of sigma are given in terms of sigma rs for already defined sigma rs. Now, after defining a vector valued random variable, we need to evaluate the matrix 2 cross 3 matrix G, that is a matrix G with elements del Gi, the partial derivative of Gi with respect to uj, evaluated at mu3, mu2, mu4, and a straightforward algebra gives the 2 cross 3 matrix G as given in the text. Therefore, we obtain the large sample the asymptotic joint distribution of G1 and G2 as bivariate normal with mean vector 0 and dispersion matrix sigma psi, where psi is defined as G sigma G dash, that is transpose of G. The exact expression of psi requires a huge calculation and hence we skip the details. However, if the underlying distribution is standard normal, then a tremendous simplification is possible, because in such a case mu3 equal to 0, mu5 equal to 0, mu7 equal to 0, and mu4 equal to 3, mu6 equal to 15, and mu8 equal to 105, and hence we obtain sigma in a very simplified form, which is a matrix with elements 2, 0 and 12 in the first row. Then the second row consists of 0, 6 and 0, and the third row consists of 0, 0 and 108. And using these values of mu2, mu4 and others, we obtain G matrix in a very simple form, which is with elements in the first row as 0, 1, 0 and minus 6, 0, 1 as the elements in the second row. Thus, combining all these, we find the large sample distribution of G1 and G2 as a bivariate normal with mean 0 and dispersion matrix as a diagonal matrix with diagonal elements 6 and 24. Thus, we find that the sample skewness and Cartosis coefficients are asymptotically independent if the underlying distribution is normal. However, one can check that if the underlying distribution is symmetric about the origin with finite even order moments up to and including the order 8, independence hold. So the above result is not limited to normal distribution. This result can be extended for any symmetric distributions with symmetry about the origin. However, in such a case, the asymptotic variance will be different from 6 and 24. Next, we pass on to bivariate distributions. So our next example, in our next example, we find the large sample distribution of sample correlation coefficients. So we start with IID random vectors xi, yi with finite 4th order moments for x and y both. So define the correlation coefficient based on n pairs of observations by r equal to sxy divided by square root of sxx multiplied by syy, where sxy is the sample variance covariance measure which is defined as 1 by n summation I from 1 to n xi minus x bar multiplied by yi minus y bar. Naturally, Rn is invariant to location transformation, and hence without any loss of generality we can assume expectations of xi and yi as 0. Now we define for non-negative integers r and s mu rs as expected value of x1 to the power r multiplied by y1 to the power s, and mrs as 1 by n summation I from 1 to n xi to the power r yi to the power s. Then Sxy can be expressed as m11 minus m10 multiplied by m01. Sxs is nothing but m20 minus m square 10, and Syy is nothing but m02 minus m square 01. Thus, we observe that Rn is a function of 5 moments, namely m11, m20, m02, m01 and m10. Now, it follows from the central limit theorem that the large sample distribution of these 5 moments is a 5-variate normal with mean vector 0 and dispersion matrix sigma, where dispersion matrix sigma is nothing but the dispersion matrix of the vector with components x1, y1, x1 square, y1 square and x1, y1. Naturally, mu01 and mu10 are all identical to 0. So, looking at the expression of R as a function of 5 moments, we define the vector valued function g, which has 5 arguments u1 up to u5 as a 3 component vector with elements u3 minus u1 square, then u4 minus u2 square, and the last element is u5 minus u1 multiplied by u2. Thus, with the already introduced notations, we have to evaluate in this case a 3 cross 5 matrix G at the expectation, and a straightforward algebra gives G as a partition matrix where the first part is a 0 matrix of order 3 cross 2 and the rest is an identity matrix of order 3. Hence, applying delta theorem, we get the large sample distribution of Sxx, Syy and Sxy as a 3-variate normal with mean vector 0 and dispersion matrix G sigma G dash. Now, a simple matrix calculation yields expresses G sigma G dash as the dispersion matrix for the vector with elements x1 square, y1 square, x1, y1. Thus, we have obtained the joint asymptotic distribution of Sxx, Syy and Sxy. So, at this point, it should be remembered that we have expressed R as a function of 5 moments. Then, from 5 moments, we have identified 3 distinct quantities Sxx, Syy and Sxy, and we have obtained the large sample distribution of Sxx, Syy and Sxy. So, now our task is to find the distribution of R using the joint distribution of this Sxx, Syy and Sxy. So, we define the univariate function h with 3 arguments u1, u2, u3 as u3 divided by square root of u1, u2. Then, a simple algebra gives the gradient vector of h evaluated at the expectation as a vector with 3 components with elements minus rho divided by 2 mu 2 0, then minus rho divided by 2 mu 0 2, and the last element is 1 by square root of mu 2 0 multiplied by mu 0 2, where rho is the population correlation coefficient defined by mu 1 1 divided by mu 2 0 minus, the correlation coefficient is defined as the rho is the population correlation coefficient. Thus, by delta theorem, after some little bit calculation, we find that Rm, the sample correlation coefficient, has a large sample distribution with mean rho and variance, large sample variance sigma square, where sigma square has a cumbersome expression as given in the text. However, to obtain the exact expression of sigma square, we need to perform the above matrix multiplication, and hence we omit the details because it is very straightforward. So, naturally, the large sample variance depends on the unknown moments of the underlying distribution. However, the expression for the underlying distribution as bivariate normal is of special interest. Thus, we assume that the joint distribution is bivariate normal with correlation coefficient rho. Then, we need to derive the expression of dispersion matrix for the vector with elements x1 square, y1 square, x1, y1 under bivariate normal assumption. It is easy to observe that variance of x1 square and variance of y1 square are exactly equal to 2. This follows from the fact that x1 has a standard normal distribution marginally. So, x1 square is a chi-square distribution, has a chi-square distribution with 1 degree of freedom, and hence the variance of a chi-square distribution is 2. Next, the covariance between x1 square and y1 square can be expressed as expectation of x1 square y1 square minus 1. Now, if we apply the fact that the conditional distribution of y1 given x1 is univariate normal with mean rho x1 and variance 1 minus rho square, we simply obtain that expected value of x1 square multiplied by y1 square is nothing but 1 plus 2 rho square, and hence we get the covariance between x1 square and y1 square as 2 rho square. Now applying similar arguments and the fact that the distributions of x1 and y1 is exchangeable, that is the distribution of x1 y1 and the distribution of y1 x1 are the same. So we get expected that the covariance between x1 square and x1 y1 as twice rho, which is also equal to covariance between y1 square and x1 y1. And finally, looking at the fact that variance of x1 y1 equal to expected value of x1 square multiplied by y1 square minus rho square, we find this as 1 plus rho square. Thus we finally get the dispersion matrix for the vector with elements x1 square, y1 square and x1 y1 as a 3 cross 3 matrix with elements 2 rho square and 2 rho in the first row. Then we have elements 2 rho square, 2 and 2 rho in the second row, and finally we have the elements 2 rho and 1 plus rho square. Again, for a bivariate normal parent, we get the gradient vector as a 3 component vector with elements minus rho by 2 and 1, and then a simple matrix multiplication gives the result that the large sample distribution of Rn, that is correlation coefficient, is univariate normal with mean rho and variance 1 minus rho square whole square. So now we shall start a simple interesting study regarding the behavior of R in small samples and large samples. After getting the asymptotic distribution, it is natural to study the rate of convergence. So in other words, we need an idea about the value of the sample size ensuring asymptotic normality. For numerical evaluation, we assume a bivariate normal parent with correlation coefficient rho equal to 0. For rho equal to 0, it is well known that R multiplied by square root of n minus 2 divided by square root of 1 minus r square has a t distribution with degrees of freedom n minus 2. Then it is natural to compare the asymptotic distribution with the actual. Hence, we provide the normal QQ plot of the variables t1n and t2n, where t1n is defined as square root of n multiplied by r minus rho divided by 1 minus rho square, and t2n as r multiplied by square root of n minus 2 divided by square root of 1 minus r square. Actually, we have standardized our large sample distribution, our large sample variable, and kept it in t1n. Now we shall obtain the QQ plot for n equal to 15, 20 and different values of n based on a simulation study, and the plots can be found in the next page. So for n equal to 15, the plot is given in the next page. The left figure is corresponding to t1 and the right figure is corresponding to t2. In the next page, one can also find the same thing for n equal to 20 and for the variables t1 and t2 both. So what do you observe? Looking at the figures, we find that asymptotic normality holds even for n equal to 15 or 20. Thus, inferential procedures for n equal to 15 or 20 observations can be based on this approximation, and one can assure that the loss will be very little. However, it is interesting to observe that the second variable whose exact distribution is t under a bivariate normal parent is also very close to a standard normal for those sample sizes. But the results obtained for rho equal to 0 cannot be stated in a generalized way, and we may have some distributions which is different from bivariate normal, and in such a case the exact distribution of t2n is not known, and hence that exact t distribution or taking this variable is of no use. Next, we shall study the convergence rate for bivariate normal parent. After getting the asymptotic distribution, it is natural to study the rate of convergence. In other words, we need an idea about the value of the sample size ensuring asymptotic normality. For numerical evaluation, we assume a bivariate normal parent with correlation coefficient rho equal to 0.5 and generate the standardized variable square root of n multiplied by r minus rho divided by 1 minus rho square for different values of n, and construct the normal QQ plot. These plots can be found in the next page. So For rho equal to 0.5, we have considered 3 values of n, namely 60, 90 and 120, and for each value we have provided the normal QQ plot, and this can be found in this page. So looking at the figures, what do you observe? This QQ plots tell us that as we increase n, that is the sample size, the convergence becomes better. That is, the limiting distribution becomes closer to the standard normal distribution. For n equal to 120, we find that the approximation is good enough. However, we have used the theoretical value of rho, and hence the asymptotic variance to generate the QQ plot of T1n. But in practice, asymptotic variance is not known, and hence to be replaced by suitable estimates. Such replacement, of course, makes the convergence rate slower. Next, we consider a non-normal bivariate parent. That is, we use a bivariate gamma distribution. So we have just discussed the convergence to normality for bivariate normal parent, but distribution can be non-normal also. So we consider a particular type of bivariate distribution, namely Mach-K gamma distribution, defined by the density as given in the slide. So it should be noted that for such a distribution, the correlation coefficient is simply square root of a divided by a plus b. That is, for such a distribution, correlation coefficient is always positive. Thus, to study the convergence rate for non-normal parent, we perform a simulation study with a equal to 1, b equal to 3 and c equal to 2 for different values of n. And this a, b, c are the distribution parameters defined in the PDF. In particular, we prepare histograms of square root of n r minus 0.5 for different choices of n based on samples from bivariate gamma distribution, and all this can be found in the next page. So for bivariate gamma parent, we have generated the histograms for n equal to 100, 150 and 200. It should be noted that we have chosen parameters a and b in such a way that rho equal to 0.5 is satisfied. We have already studied such a behavior for bivariate normal parent. However, for bivariate gamma parent, the asymptotic variance calculation requires knowledge of the higher order moments, and hence for brevity we provide only the histogram. The histogram for n equal to 100 shows a considerable amount of skewness. However, the extent of skewness diminishes as we increase n from 100 to 200. For n equal to 200, we arrive at the histogram of a symmetric distribution. Such a phenomena was observed for bivariate normal parent with smaller sizes. Thus, one can conclude that non-normal parent makes the rate of convergence slower. Next, we consider a discrete parent, that is a multinomial distribution. So we have discussed so far convergence considering a continuous bivariate parent, but the underlying distribution can be discrete as well. So we know, to know the rate of convergence for such parents, we consider a multinomial distribution with parameters n, p1 and p2, and prepare a histogram of the quantity square root of n r plus square root of p1 p2 divided by 1 minus p1 1 minus p2 for known values of p1 p2 and increasing values of n. The values of p1 p2 are chosen in such a way to reflect high, moderate and low correlation coefficients. For each value of p1 p2, we simulate the value of the above quantity, taking n as 40 and 80, and all this can be found in our next few slides. So in our first figure, we have histograms for p1 equal to 0.1 and p2 equal to 0.2 and n as 40 and 50. In the second figure, the parameters are p1 equal to 0.2, p2 equal to 0.3, and for the third figure, p1 is 0.3 and p2 is 0.4. And finally, we have convergence to normality for p1 equal to 0.4 and p2 equal to 0.5 for both n equal to 40 and 50. So what we observe? We have fixed parameters in such a way that rho takes the values minus 0.17, minus 0.33 and minus 0.53 and minus 0.82. As expected, with the increase of n, the histogram closely represents a symmetric distribution. However, the height of the histogram increases with the increase in the theoretical correlation coefficient. Naturally, the spread reduces with such an increase. Thus, it is easy to say that the variability of the asymptotic distribution decreases with increase in the correlation coefficient value. Thus, for discrete bivariate parent, the variability of the asymptotic distribution is expected to depend on the theoretical correlation coefficient. So we have just seen the large sample distribution of sample Cartosis coefficient and joint distribution of sample skewness and Cartosis coefficients, and obtained the interesting result that under a normality of the parent, this skewness coefficient and Cartosis coefficients are asymptotically independent. We have also derived the large sample distribution of correlation coefficient and also simplified the expression for a bivariate normal parent. However, we have also investigated the nature of correlation coefficient for different values of n when the parent is non-normal, especially when the parent distribution is bivariate gamma of Mackay's form and multinomial with two categories. And finally, we concluded with the discussion that non-normality reduces the rate of convergence for correlation coefficient. In our next module, we shall discuss asymptotic distribution of different quantiles and different summary measures based on quantiles.